This video is going to be a continuation of our part 1 video on applying properties of rational exponents and simplifying radical expressions. So we've got a big doozy of a radical expression here. The fifth root of 320 x to the 7th, y to the 12th, z to the 10th. A lot of stuff going on here. So we've added variables along with the number part. I'd say take this a piece at a time. And again, I'll show you a couple ways of going about doing this. So first method, I'm going to go ahead and look at just the number itself, the 320 part, and think to myself, how do I simplify the fifth root of 320? Any perfect fifth powers? Well, my table doesn't have the perfect fifth powers, which is kind of too bad. But maybe, I don't know, maybe I know that 32 is 2 to the 5th. That would be useful if I were to know that. Just check it out to make sure. 32 times 10 is what I'd have going on there. So I'd have the fifth root of 32 and the fifth root of 10. The fifth root of 32 is indeed 2 because 2 to the 5th power is equal to 32. So I have 2 times the fifth root of 10. Now I've also got all these variable things that I need to deal with. Okay. When you're dealing with variables, I often will start with this method of writing out all the factors. It gets a little bit messy, but maybe you can catch what's going on here. I'm going to have the fifth root of a huge radical sign. 320 we already figured out is going to be this 2 times the fifth root of 10 business, so I'm just going to put a 10 here, understanding that there's a 2 on the outside. Now for the variables, x to the 7th, well that means I've got 7 x's. 3, 4, 5, 6, 7. Then I have 12 y's. 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, and 10 z's. 1, 2, 3, 4, 5, 6, 7, 8, 9, and 10. A lot of stuff to write out, but now you'll see what goes on here. I'm looking for perfect fifth powers. A perfect fifth power is the product of 5 identical factors, so I'm going to look for groups of 5 factors here. I see that I've got 1, 2, 3, 4, 5 x's. 5 x's means I can take out 1 x. Then I've got, let's see, 1, 2, 3, 4, 5 y's once. And 1, 2, 3, 4, 5 y's a second time. That means that I can take out 2 y's. And when I say take out, I'm factoring them out, and all these things will be multiplied together. So I'm going to have a 2 times 1x times 2 y's. Well, 2 y's multiplied together will become y squared. Still have to do the z's. 1, 2, 3, 4, 5 z's here. 1, 2, 3, 4, 5 more z's here, which means I have z squared that comes out of there. So 2xy squared z squared times the fifth root of, then I put inside the radical anything that's left over. Well, there's a 10 left over, and there's 2 x's, which means I've got x squared inside the radical, and there's 2 y's, which means I got a y squared, and the z's I took care of. So this would be my simplified algebraic expression right here. No perfect fifth roots. There are no perfect fifth powers, excuse me, in the radicand. Only one variable on the outside and inside. So I'll repeat stuff that I put together. This is good to go. So now, in order to get to this the x squared y squared business, there'd be an easier way than writing out all of the variables. So let me copy this and show you what I mean. So when I wrote out the fifth root of 320, I took care of that. I had the fifth root of 320 was 2. Oops, I don't want to use that pen. Fifth root of 320 was at 2 times the fifth root of 10. Now if I had to figure out the rest of the variable parts, I could write all these things out in circle groups, or you'll notice, if I took the exponent, 7 in this case, and divided it by the index of the radical, 5. Well, 5 goes into 7 one time, which means I'm going to take out 1x. Now, if I were to divide 7 by 5, I would get 1 with a remainder of 2. Well, that means that there are 2 x's left over inside. So I got 10x squared. I can do the same for the y's. Well, y to the 12th, and then take the fifth root of that. Well, let's see, there's 12 y's. 5 goes into 12 twice. So I take out a y squared, and that'd leave me with 2 leftover y's. So y squared would be inside the radicand. I'm going to do the last one with z to the 10th. Same thing. Take 10 divided by 5. Well, that's going to be 2. So z squared comes out. And it's 10 divided by 5 is 2 with no remainder. Excuse me, which means that z doesn't need to show up in the radicand. And you'll notice this is the same expression that we circled over here. So just another big example of simplifying radical expressions.